Welcome, everybody, to Dallas Personal Robotics Group Robot Builders Night Virtual for Tuesday, June 16th, 2026. Tonight, we will do our normal presentations of robot projects and then open the floor for any questions or comments. A little bit about housekeeping. A reminder that Moon Day 2026 will take place July 18th at the Frontiers of Flight Museum. DPRG is looking for volunteers to attend and show off their projects. The other business I had is already gone by. It was the power lunch. Maybe Paul can talk a little bit about that later on as well. First presenter we have is Ray.
Hello. For tonight's demonstration, I'm going to blink an LED with an Arduino. Okay. Let's see here. We can get this to work. I'm going to try to use my phone as the camera. See if I can switch cameras. Output. Views. Here.
We see you.
We see you, Ray. We're not hearing you.
I went to Skechers to get that.
Nope, not hearing you.
Okay, how about now?
Yep. We heard that.
Come on there, cut that out. Okay, there we go. I want to switch my camera, but can't seem to do that. Frustrating. Does that do it? Nope. Okay. Darn it. Okay. I'm going to get off my phone. I don't think I can now. I'm not going to be able to see what you're seeing. Okay.
Yes, we'll give him a minute to see if he connects back up.
Situational. We're getting very connected to people.
You are muted, Ray.
You can hear me now?
Yeah.
Yeah, okay. Anyway, what I was doing, I actually got a platform together that's got, I can show that to you. Yep. Okay. Yep. Oop, there it is. Anyway, those are two hoverboard motors with the two three-phase brushless motor driver boards that I think you guys are planning to use to control the motors that actually spin the blades on the mowers that you got. And so right now I'm just using a potentiometer to set a voltage, and it basically spits out what how many pulses in a 50 millisecond interval that it sees, which is kind of low. 50 milliseconds, around 1/4 of the PWM range, maybe PWM of maybe 250 or so. It only puts out like 13 pulses that it sees, so it's kind of low for an encoder count. I don't know if I could. I'm gonna give it a try here. Oops. Hold on. Oh, that's popped up. Okay, I'm going to try to present a window. Share. Okay. Can you see that?
Yep.
Okay. Anyway, so it's a pretty simple program. It just sets, there's a left encoder, right encoder, variable 0, sets the direction for the two motors. Starts out with the PWM as 0 and the brake off because it's active high, so 0. And it's just a really simple loop and just prints out a bunch of the values that that there are. So I can show it running here. Okay, let's see. Okay, yeah, I don't, you see the variables, Val? Is
Yep.
that, yeah, okay, so that's like right now 1/4 of the range, and I'm going to turn it down to 0. Yep. Okay. Okay, it's bouncing around a little bit, but that's okay. Anyway, as I turn that on.
So do you have a motor spinning here, Ray?
Yeah. The and what Hoverboard did, actually 2 motors, but Hoverboard had these it's like, where is it? There it is. They actually have like an LED array inside the wheels, and when you energize the wheel, it's like inductively coupling to the LEDs.
Huh.
And spinning the wheels. So they're not, it's not too bad. There is, okay, that's like maybe 1/8 of the speed or so. And if I crank it up, it seems pretty smooth, pretty repeatable. Okay, that's about 1/4 of the PWM range. Let's see. It probably doesn't, you can just see the wheels spinning. I haven't, tested it out to see, how much torque it actually produces. I'm hoping, I'm going to try it with, the mower with with these motors, I'm going to start out with 2 and see if it has enough traction, and possibly go to 4. And I've also, hold on a second. Put the encoders in the and 3D printed. I'm going to make that big. That is not very big at all. Yep. Okay. Okay. Anyway, so I just 3D printed a little shell that holds one of the Pololu magnetic encoders. There's like 10, I think 10 poles. And so you can get, you know, in quadrature, you're going to get 10 poles for, you know, the A output and the B output, or 10 pulses rather. So basically took off what he had on the back of the motor and replaced it with my own 3D printed version of it, like an end cap. So, and those are the 4 encoder motors, or encoder wires, and those are the 2 power wires. So if these motors are good enough, strong enough, right RPM, then I'll probably use those. If I can't get enough traction, or if, you know, it gets stuck in the grass a lot, I think I'm going to try 4 of the scooter motor. So it'll be like 4-wheel drive. So
Hey, Greg,
yeah.
Could you, okay, when you opened it up and you looked in the back of it, you know,
Yeah.
the Pololu ones are made to slip onto the motor lead terminals. Did you make like a 3D print and not mount it to the motor back?
Yeah, it's super glued to the basically an elevated platform on the inside of the encoder.
Okay.
And I don't know if I can pop one off here.
That would be cool. Do you know what was the getting an encoder with the magnet with the proper hole in it, was that easy or hard, or did you have to drill it, or which is hard, very hard?
Yeah, I had to drill it out. It's just these, the original hole is really pretty small for the those little things. So the motor shaft is 5 millimeters, and that's like maybe a 2 millimeter hole, maybe bigger, 2.5 millimeters. Anyway, if you're careful, you can do it.
You showed the innards of it last week.
Yeah,
it's on the video, Doug. It's worth taking a look at. It's pretty cool. Yeah.
But anyway, so it gives it, if you don't look at both edges, you have 700 pulses per wheel revolution. If you look at both, then you have 1,400, which is
funny.
Seemed like too much. So it, you know, you could do it with one interrupt and just sense the other line, whether it was high or low, and do it that way and not look at both edges. And
hey, Ray, when you pull the sensory encoder implementation off, how would they built their encoder? Because it's just a single channel encoder, but what was it?
He's got a Hall effect sensor in it, and it's I can show you. Hold on. It's a little skinny magnet.
Okay. I've always wondered what was in there.
Find where I put it. Oh, there it is. Okay.
I took one apart, Paul, and he probably changed design from motor to motor as they were doing it. And some of them prototype. The one I had just had a bar across.
Okay. This there's actually a hole
So just
drilled perpendicular to the shaft, and that little teeny magnet is in it, and that scans across.
Oh,
He's got a, I don't know if you can see that or not. There's a little teeny square cut out, and that's where the
Ray, we can't see it. Put it in front of your face.
Oh, okay.
In front of your face.
Put it in front of my face. Okay.
Yeah, yeah.
Okay.
We can't see it when you hold it up to the side.
Oh, okay. I don't know if you can see that little slit, but there's a Hall effect sensor in there,
Okay.
and it's soldered to. He's got a little printed circuit board on the back.
Your face, guy.
But the Hall effect sensor is really small. Let's see. Do I have one out here?
how is the magnet held onto the shaft?
It looks like, yeah, the Hall effect sensors are like that size. They are very small.
Mm-hmm.
Mm-hmm.
It looks like it was just like a really tight fit and looked like it had some super glue on it.
Oh, okay.
So, but you can just force it out
Okay.
without, too much pressure. I scratched off the super glue first, whatever I could see, and then just pushed on it a little with a pair of pliers, and it popped right out. Some of them had this little piece of plastic that actually held it in place. Let's see if I can get it to go back in. Yeah, so that actually fit around the little magnet, that little piece of plastic, and then went around the shaft. If you can see that part of it, but then that was easy to pop off too. So
Cool. Thanks.
So the magnet spun axially around the shaft.
Yeah, this, if that's the shaft, the magnet was pushed right through it, and spun in front of the Hall sensor. But it, that was only 1 pulse per revolution. So,
Thanks.
but anyway, so if anybody's interested, I can send out the STL files for the shells and stuff. And I just there's nothing on the back of the motor that you can, there's not like a threaded hole or something. So I just super glued this. There's like a pretty large flat area, and to get it so it was concentric, there's also a little piece of it looks like it holds the bearing. So it fit tight around that. So it was, it may be a 0.5 millimeter off, but it's close enough for Hall effect sensors and, all that to still work out. And so I spun the motors up, applied, like 24 volts to it, and the waveforms still look pretty good. So I figured, I don't know if they'll ever be spinning that, with full 24 volts and just, like the no load RPM, basically. They'll probably be a lot slower than that. So I figured it should work okay. Don't know what it's going to do over temperature, but I think the Hall effect sensors were pretty good. I think some of them even had temperature compensation in them, but I don't know which ones Pololu used on their encoders. But anyway, it looks promising. The little hoverboard motors are pretty torquey. I just, at this point, I don't know how torquey it needs to be and whether it's going to be torquey enough. So I'm kind of trying them both, and the DC motor and the 3-phase brushless motor. And if 2 won't work, I'll go to 4. So. But anyway, so that was all I had.
Ray, one last question. On
Sure.
on the brushless motor, there's really hub motors, aren't they?
Yeah, I think they would be considered hub motors, because the They just have a shaft that sticks out. It's a hollow shaft. That's what all the wires come through.
Yeah.
I don't know, maybe 2¼ to 2.5 inches long. And there's a flat machined on it. So, and 2 of the metal pieces that came out of the scooter, you could use to secure them down with. Let's see. I don't know if you can see them. Where I can't even see what I'm looking at here. Yeah, I don't know if you can see those 2 metal pieces at the end of the shaft there
Okay.
or not. But they're pretty thick steel, maybe 1/8 of an inch thick, and they're, you know, stamped to mate with the shaft.
Okay.
So, and this is just, I'm guessing ABS plastic. It's like a pretty large U channel.
Mhm.
And so, you know, I need to mount it a lot more rigidly on the mower because it's going to be supporting a lot more weight.
Can you change the wheels?
I changed the wheels. What do you mean?
The tires, I should say. Can you
Oh,
change?
no, they were the original tires.
No, but I mean, can you? If you wanted one different, a different grip or something like that.
Yeah, I think I've seen them on AliExpress. I've also seen some YouTube videos where people take a pneumatic tire and actually, well, I've seen it both ways. On some of the ones where there's enough room to do it, they actually drill a hole for the stem of the inner tube to go through. And other ones, they actually drill a hole in the side of the tire
Well,
for the stem to come through. And I want to say like a 4-inch ID tire fits on the hubs pretty good. You know, the tire part of that you can pry it off basically.
that's what I was asking. Yeah.
Yeah. So you can put bigger ones on it. 2 of the hoverboards have the same sized wheels. The other hoverboard that I got, it's got more like it actually does have a pneumatic tire on it, and it's got more like a 12-inch wheel. And these 2 of the hoverboards ran on 24 volts, and the one with the larger wheels runs on 36 volts. So that's my hoverboard, the extent of my hoverboard collection so far. That's all I have. So anyway, so it's kind of neat to get it to go. You probably, you know, if you guys are going to use them as mower blade motor drivers, you know, it should go pretty smoothly. The boards do not do speed regulation. So if you have a fixed PWM and you increase the load on the wheel, it'll slow down. You know, you've got to close the loop and look at, you know, either the pulse width or the number of counts, which is kind of crude, to, you know, kind of maintain velocity or speed.
Yeah, I'm planning to use that pulse that comes out of the motor controller and use that to close the loop.
Yeah. Initially, I thought, you know, well, it'd be great if this thing does, you know, like velocity control, you know.
The control. Yeah, no such luck.
Nope. So anyway, that was all I had.
Well, thanks, Ray. That interesting. Making some progress.
Yeah, finally.
Okay. Next up, we have Paul.
Yeah. I've been working very hard. I've spent a month of my life on checking out LC, the Quectel or WaveShare LC 29H RTK GPS receiver, and done a lot of work on it. And so I finally got, so I wrote it, I took someone's driver and made it ROS compatible, improved its ROS style. And today—
Pat, can you mute? Can you self-mute, Pat? Thanks. Sorry, Ro. Sorry.
And so just perhaps a quick overview of the LC29H. It's got a WaveShare. This thing's $73, so very reasonable. And that comes with the antenna compared to like 300 something for the U-Blox ZF9P. And it's designed to fit on top of a Raspberry Pi. It'll fit on there's a Pi 4, I think. It'll fit on a Pi 0 as well. So it just uses the serial port, one of the serial ports on the Raspberry Pi connector. So I did a bunch of documentation here. I'm going to paste this into the chat, the link to the repo where I've put the LC29H DA RTK GPS driver. And so, started with someone else's work and improved it. But it comes in two flavors, a BS flavor and a DA flavor. The BS is intended for use as a base station. The DA is intended for use as a rover, and they're not interchangeable. You can buy them off Amazon. They're about on about a 30-day lead, about a 3-week lead time. But because they come from China, but they actually came ahead of schedule. So I actually got mine in about 2 weeks. Kareem had a similar experience, and so I got instructions on how to run the driver, what topics it publishes, the parameters. There's an XY node that subtracts the a local origin from the fix to give you an offset, an XY offset from the local origin, and examples of how to run it. There's a print position command and so forth. So on a launch file that starts the driver and the XY node and an Entrep client. So the assumption here is, there's what you need to be aware of. This is an L1, L5 GPS receiver. And so it's got some pros and cons. It's cheaper because I don't know why L5 is cheaper, but it is. But there aren't many stations on the internet broadcasting L5 corrections, and you really want them for this. Fortunately, or maybe unfortunately for me, I'd gone through a lot of work to document how to set up the base station version of this. And that documentation is right at the top here. Information about the base station, how to set up system as a whole in this repo here. And there's, I'm up to like 15 pages, but it includes testing results. So overview and software and how to use the Windows app to connect to the base station and what messages it supports and how you survey in, because the wiki, the WaveShare wiki is incorrect on how to do a survey in. but this approach works. So do you need a base station? Well, you need one if you can't get corrections off the internet, if you're too far away from an internet base station. So I don't know if Ray would need one. I'm close enough to a mount point called VN1 that's in North Dallas at the US 75 and Spring Valley kind of area. So I've been using their corrections pulled off the internet. But before I became aware that that was available, I actually went through this whole procedure of setting up a base station and setting up a caster. And so it's all documented here on how to set up a Linux Ntrip server that pushes corrections to RTK to go, and useful base station commands. So I've been testing it, and that's where I think I'll spend a lot of time today. So for a while I had antennas.
Paul, before you leave the subject of the base station, just to let people know, the VN1 didn't add L5 until just a couple of weeks ago. So, Paul, you would have ended up going through that process anyhow. There are still legitimate reasons to go and set up your own base station. And you don't have to use an Ntrip server to get the data to it. There are other ways to do it, but Ntrip is probably the most common way, and you can get a free version of the SNP server to run locally if you don't want to go through RTK to go. So RTK to go is that internet service that gives you, like if your robot doesn't have an internet connection, right, then you can use some other method like wireless radios to get it onto your robot. But Paul's repo doesn't provide a way to do that right now. It would be, in other words, it would be your responsibility to get the correction data into the receiver somehow.
Yeah.
But the main reason to run your own base station is RTK to go goes down every once in a while, and sometimes it's pretty bad.
Yeah.
And so all of a sudden you're without a correction source, and you go more than a few minutes without correction, and you're going to dwindle back to regular old GPS very quickly.
Yep.
So what was your connection method, Paul? Was it that you talked about like
I've got.
radio?
I'll show you here in a tick. I've got a cellular.
Oh, okay.
But what so I've got testing results here, and I'll tell you what. Let me just skip over first to the contraption. So I wanted to compare. Let's see, I'll pin myself, and oh, I am pinned. Good. Carl Ott would be proud of me. I built something out of duct tape and baling wire that is a comparison test unit using a ZF9, a ZF9P right next to an LC29H, and I'm running them both on the same mobile assembly. So this is my comparison. So it's mounted on a tripod. Here's the duct tape holding the battery on, so I could take it around my yard. And there's a little, just plug this cellular modem in to the USB on the Raspberry Pi, and it looks like it's got an Ethernet attached to it, and that connects to the internet. And so then I can get corrections, and I can also go off to get into it from my home network using VPN. So continuing on this monstrosity, we've got the ZF9 antenna and the LC29 LC29H antenna. And then this is the electronics board off of Mowberry. The main thing I'm using is the Raspberry Pi, and plugged into the Raspberry Pi are the two GPS boards. Let's see if we can you can see the red one is the ZF9P, and the blue one is the LC29H. So this is real hacked together, but it's
Nonsense. I see your fully shock hardened, military grade, weather resistant. That's a great setup there.
all of that, Kareem. Carl would be proud of me.
I don't see the baling wire.
No, there's no baling wire, but there is string. The battery is held on with
All right,
string.
good.
So
good.
maybe
Zip
that-
tie.
It's got a string.
Yeah.
It's got a string. That's better than baling wire.
So
Rubber bands too.
so I took this thing out, and so what I wanted to do was, I put all this software together and the driver and documentation and everything, but I still didn't know whether the darn thing worked properly. And so that's what I want to talk about today, because I had a second purpose for this. I recently had my yard surveyed, and I think one of the points was off. So I wanted to resurvey my yard and compare it with what the surveyor produced, and using RTK to go. And I also wanted to check whether the LC29H was as good as the ZF9P, better, worse, whatever. So let's see. Let me switch to sharing my screen again. So this is my place, and so I'm going to walk through. Actually, I want to share something different. I want to share this screen, and I'm going to pop this over. This is coming through okay, right?
Yeah.
There we go. Okay, so there's a Corps of Engineers monument down under a steel H bar here, a first corner marker up behind the Hobie, a second corner marker under the tree, a third one next to the neighbor's house, just over here, and then another one in the middle under this tree, and another one on the corner that's clear of trees. So I'm doing several things here. I'm comparing two different RTK receivers in a variety of conditions, from open sky to under trees. There's another corner marker here, and another one here next to this big hedge, and then another one under these crepe myrtles, and then the last one is down in this corner before you get back to the Corps of Engineers marker. And so I have this survey, and the survey starts at the Corps of Engineers survey marker down here and goes around in a clockwise direction around the points that I just showed. So here's where the cottonwood tree is here. I'm shading this one. Then this is in front of the neighbor's house. This is by the street, the other end of my yard by the street, back under the crepe myrtles, and then back out to the corner by the lake. And so there's my assembly, and here it is in the Corps of Engineers marker. And you can see on the ground there's this monument, survey monument, which is not accurately positioned by the Corps, but at least it's some kind of permanent monument to use as a reference. So I took this whole assembly around, because it's self-contained, it's got a battery, and it's got cellular connection to the internet. And with VPN over that, I could get to it from my laptop that was on my home network, and read off the readings from the position from the ZF9P receiver and from the LC29H receiver. And so here's another a marker in open sky. That's a second marker. Then this one is, here it is under the cottonwood tree, just about pretty much shaded by it. Then here it is in front of the neighbor's house, and here's the next survey marker that's under the neighbor's tree. And then we go on around to the front where it's pretty much in the open by the street, middle of my front yard, the other corner by a big bush here, and then under some crepe myrtle trees, which proved to be a significant issue. And then finally, the final corner is up around where this orange flag is. And so, so the system block diagram, I had the Raspberry Pi with two GPS receivers connected to it. The cellular modem was actually USB connected, so it looked like a Ethernet connection going off to the internet. Tailscale VPN going back to my laptop. The RTK2Go server is off on the internet somewhere, and as Kareem alluded to, it just gave me fits. It was down probably a third of the time that I was surveying. And so this is an annotated chart of X. This top plot is /GPS/XY/point/X is from the LC29, and the other one is from the ZF9P. So I've overlaid them, and you can see where they differ in places. And similarly for Y, this is Y, the Y offset from the local origin for both the LC29 and the ZF9P. Now this, I'm using Plot Juggler, and this is a computed graph that shows the Euclidean distance between the LC29 fix and the ZF9P fix at various points in time. So here you get
are your scales in millimeters or centimeters?
No, meters. So
meters. Oh, wow.
Yeah, so these X offsets are in meters offset from the origin. Similarly, the Y offsets are meters offset from the origin. And then these differences, delta, this Euclidean distance. And by the way, the distance between the two antennas is 10 centimeters, just pretty much on the nose. So that's what you're hoping for is a 10 centimeter difference, plus or minus 2, because RTK GPS should be accurate to 2 centimeters. You can see here that the Euclidean distance at times goes as high as 3 meters, but look at what RTK2Go was doing.
3 meters. The third one is also in meters? That's
Yes.
in centimeters or millimeters.
Meters.
That's also in meters?
Yes.
Well,
So
that's bad.
That's a huge variance.
Yeah,
and you were sending the same entropy corrections to both receivers simultaneously?
Well, no. Let me finish, Kareem. Let me finish.
Okay. All right.
This bottom plot is HX. That's the ZF9P's horizontal accuracy. And where you see it jump up here is where I lost corrections. And so RTK to go was up and down. So this bottom blue line is an RQT bag trace of the corrections messages / RTCM. So you can see where it's blue, I'm getting corrections messages, and you got a low line on the horizontal accuracy. And I'll pull up Plot Juggler and we'll look at the actual values here in a tick, but I'm just laying out the landscape here. Then RTK goes down and you lose corrections. The horizontal accuracy goes up. So horizontal accuracy I found to be a good proxy for no entrip, no corrections from the entrip server. So basically it was lost through this whole period. Then it was good from here through here, which let me get from the Corps of Engineers monument to the first marker, and then on to the second marker, which is under the cottonwood, and then as far as Joe's house. So all up one side of the property. And then corrections dropped out. So if you look at the amount of blue on this whole line, I've lined these traces up so that they align with the scale. So this is a little over 2 hours of surveying. And I would say that probably a third of the time there were no corrections. And I was just like waiting for RTK to go to come back. You know, and the driver tells you, or the Entrip client tells you that there's no correction. So that's the reason why I'm seeing 3 meter deviations, Kareem, is both receivers are dropping back to plain old GPS.
Sure. Yeah.
But then where I do have good corrections, that's where it gets interesting. And I'll dig into that in a little more detail here in a bit. But I've annotated, you know, going around the property and one like here is very interesting because it's under the crepe myrtle. It never could settle down under the crepe myrtle, and we're like a little over ½ meter while it's sitting actually under a dense foliage cover from the crepe myrtle. Okay, so that's the high level. So let me just then bring up.
Yeah, I think certain leaves of certain trees are like a quarter wavelength of the, you know, base frequency or whatever that GPS uses. So
Yeah.
it probably acts as a shield.
Yeah. So so this is Plot Juggler, and starting out from, so you can kind of see when I move, you get this big spike because in Euclidean distance between the antennas, because as I'm walking, the fixes are coming in at different times from the two receivers. So they're reporting different positions. And you can also tell when I move from the step jumps in the X and Y. So, you know, this is going from Corps of Engineers to the first marker, then to the marker under the cottonwood, and then to the front of my neighbor's house. So that, but that's what causes these 1.5 meter spikes is while I'm walking. But now the interesting thing to look at is when it's stationary, what is the delta? So that's what I want to bring up. And so can you guys read this little 0.156 here? Maybe if you unpin me, because I don't need to be pinned for anything more. And so that this becomes bigger for you. Can you see that this is like 141 here?
Well, I can understand it is. You have to tell me. It's pretty small.
Okay, sorry, I can't make it any bigger.
That's fine.
At full screen, I can see it, but it's pretty tiny.
Okay, so when the ZF9P says the horizontal accuracy is 141, that means 1.4 centimeters. That's my experience tells me it's locked in. It's got a good GPS fix at that point. That's as good as it gets. And so then the interesting thing to look at is what's the delta between the what's the Euclidean distance between the LC29H antenna and the ZF9P antenna when horizontal accuracy says 141, 1.4 centimeters. And in this range here, while I'm at the Corps of Engineers monument, the delta is about 15 centimeters. So, okay, I believe that. That's about, they are actually 10 centimeters apart. So, and it's saying 15, we'll give them each a couple of centimeters. And yeah, I believe they've got an RTK fix. So then I walk over to the first marker around the loop, and suddenly the delta turns into 0.359. So I'm like, what is going on here? So the two receivers are now saying that their antennas are 35 centimeters apart. And if I take a look at and zoom in on this little bit in Y, you can see that Y was just nicely aligned on the two receivers, but then after I moved it to its new position, looks like I jiggled it a bit here as I settled it, then they came up with a different fix, a lot different fix. And so the blue is, well, sort of the greeny color, the top line is the LC29H reporting 29.96 centimeters, 29.96 meters offset from the origin. The orange is the ZF9 reporting 30.32. So that's 36. That's the majority of the error right there, 36 centimeters of error. Okay, so that begs the question, who's wrong? And I don't have an answer, unfortunately. But I'll say this, that the level 5, when you read about level 5 L5 GPS, it says the constellation is incomplete at this time. It's not expected to be complete until 2027, and that this may affect accuracy. So that could be one explanation. Another explanation could be that the LC29 just isn't as good at locking on and holding a one cycle accuracy in the incoming waveform. And then, after I move on away from this location, you can see that they kind of get closer together again. And so
is that how much time elapsed? Because while you were in this location, their spacing is very, very even.
Exactly. So I think.
So how long were you there? Is this seconds?
This is seconds. So 1100 to 1300 seconds, about 200, about 3 minutes. So yes, I think it suffered an integer ambiguity in the RTK fix, and it got onto the wrong cycle.
You also have to to really drill down on this, you'd have to show the number of satellites that each unit has and the subset of those that actually have correction data correlated coming in for them. That's a little more complicated to set up, but that's what you would have to see in order to get an idea of which one was more reliable. Yeah. Although I would default the same way you're leaning, that's probably the U-blocks that's going to be more reliable given the number of satellites and the longer history that company has in developing RTK algorithms. But yeah.
Yeah. And maybe if there aren't as many L5 satellites up there, then
Yeah.
they don't get fixes as often or as good a fix.
There's definitely fewer of them across all of the constellations.
Right.
You'd also want to correlate which constellations you're seeing.
Yeah. So all of this is to address the question that we all want to know: is this thing worth a darn? How accurate is it? And so let's just move on a little bit in the data. Now I'm out in front of Joe's place, and then and the accuracy is 22 centimeters. So again, the antennas are 10 centimeters apart. So there's about a 10 centimeter error there. And again, it just looks like these things are
It's a repeatable error.
24.24 to 0.46. So they're about they're reading about 22 centimeters apart in Y, and the total distance is actually in. So they have a similar kind of situation. Now,
Each time you place down your tripod, are you leveling it and are you orienting it the same way
no,
versus north?
no, I'm not.
Okay. All right.
What was surprising to me, though, was how well it did under the cottonwood tree. So the cottonwood tree is, so there's the Corps of Engineers, there's the first one after that, and then this is the cottonwood tree. So it was off by 10, there was 10 centimeters of error under the cottonwood tree. So I thought that was pretty decent. Compare that with under the crepe myrtle, which is over here, and the error went up to 0.5 meter. And you can see the horizontal accuracy started to really degrade. It's like horizontal accuracy out of the ZF9P is saying 394 now. So that would be 3 centimeters. But really, when the ZF9P goes, with horizontal accuracy goes up above like 180, you're toast. The thing's worthless. So really, once I hit the XY changes here is where I carried it from the front by the street around to the back under the crepe myrtles. And again, just to remind you of the crepe myrtles, you find my yeah, this is it under the crepe myrtle. So it is actually dead under pretty dense foliage. And so it's good data to know, okay, this is what happens. And right away you see that the ZF9 horizontal accuracy jumps from 197 to 788. It's up in the 500s, and the delta between, and it sort of tries to settle in and gets itself back down to about 30 centimeters reported between the antennas, but it never really gets there. And then an interesting thing happens. I carry it over to out from under the crepe myrtles off to an open sky area, just at the Corps of Engineers boundary, and it stays here. The horizontal accuracy is dropped down to 141 on the ZF9P, but the delta between the two antennas is reported for a time as 0.4 meters, 41, 42 centimeters, and then suddenly it locks in, it drops in to 6 centimeters. So at that point it's locked in. So let's have a look and see what happened on the y-axis around that time. Yeah, so now here, the lower line, the sort of orangey line, is the ZF9P. The bluish one is the LC29. So it looks to me like the ZF9P was off by maybe a cycle or two. So like here where they're aligned, there's like a 5 centimeter difference between them in Y. Prior to that, where they're misaligned, there's a 290 to 790, a 500 millimeter, or about half a meter difference. So looks to me like the ZF9P lost itself, lost its fix while it was under the crepe myrtles, and it took a little while. By a little while, I mean specifically from about 5,250 to 5,450, say, to 5,650. So it took about 200 seconds, so about 3 minutes for the ZF9P to find its lock again and get locked back in after sitting under that crepe myrtle. So that was kind of pretty interesting data. So, I'm going to say that since the ZF9P did a clear jump when it was in clear sky, that it was the thing that was wrong in this case.
You need a third system to figure it out.
So, yeah. So do I think this thing works decently? Along with other experiments, I'd say it's probably good to 10 centimeters. It does seem to get off a cycle here and there to me. I don't think it's as good as the ZF9P, but for $73 versus 300 and something, it sort of depends on how accurate you need to be, and for your application. So I'd say it's not junk, but I don't know whether it's it or the L5 satellite constellation that's causing it
Not
to
complete
do
yet.
what I believe is performing poorly, performing not to a level of RTK accuracy.
I love that we have this level of expectation from RTK now that is just crazy compared to normal GPS, right? It's like we're quibbling about 10 centimeters, 20 centimeters. Okay, 30 centimeters is really bad, right? It's like 30 centimeters on the face of the earth, and we're complaining about it. So yeah, for the kind of price that we're talking about, is really hard to beat. The only real downside of RTK is that you got to have that correction source. But it's like, and that ends up being as much pain as anything else, probably more pain than anything else, is stabilizing your corrections. I was like, people should be drooling at the kind of prices we're paying for this kind of accuracy these days. And yeah, it's good to profile this and know that there are variances in your expectations, and what are the things you look for in order to be certain. Because there can be cases when you're navigating around a flower bed that you really don't want to crash into with a mower. Let's be really clear. But at the same point, any particular sensor is always a concern for dropout, and your system, if it's going to be really robust, needs to have a multi-sensory localization and not rely on just one system.
Yeah.
But that's really good work, Paul. That's fantastic work. It's I think it's gonna benefit a lot of people if they flag this section, and if they're really interested in another low cost RTK sensor, they can go to this video and they're gonna see some things that will sort of teach them the ropes and know what to look out for and what's possible.
Thanks, Kareem.
I appreciate it.
Yeah, so that's the LC29.
I was kind of curious about the survey results. Do they say or guarantee that it's, you know, accurate X and Y down to a centimeter, or you know, because those, I mean, a lot of cases, you know, I know
You're talking about what a surveyor delivers you, right?
What's that?
You're talking about what a surveyor delivers you.
Yeah, yeah. I mean,
The surveyor delivers you a document that promises that they took care to make accurate measurements, which in my case, I don't think my surveyor did, because I compared his survey with my legal description of my lot, and there was 1.7 degrees off on two of the legs leading to the point that I believe is off, which is why I've been doing all this resurvey, because I think he gave me about 6 feet of my neighbor's yard. But you know,
it's more likely the original survey is off.
Probably,
right,
yeah.
right, because they didn't have access to like all of these tools. I got a new survey that they were using RTK survey grade equipment, right? And so I've got a marker planted in my lawn somewhere that gives that they purport is accurate to, you know, within 2 centimeters. But it depends on the methodology that you use. If you have a house that was built in the 50s, you know, they had a different method of arriving at these things. And sometimes it's like they're going from a tree stump, an old tree stump, from one location to another or whatever. It's like they're looking at real physical landmarks. And you compare your neighbor's survey with your own, and there's always overlap in the fence lines.
Yes.
They are not high grade. They're for legal purposes to differentiate between what one person believes and another person believes, and so you can reconcile the differences. But it's very recent that we're that surveying is really at a level of accuracy that the technology can provide now.
Yes.
Yeah, my father-in-law's neighbor had put in a driveway, and it actually went like 3 feet over the property boundary. And he realized that later on when he, you know, was putting up a fence and, you know, using the fences. It's like, wow, that is way off.
And I'm about to put a shed in, and I want to make sure it's on my property. And really, the legal definition is what you've got in your warranty deed, and it's only legal as far as the title company will pay you some money or buy a slice of your neighbor's land if what it says is proven to be at odds with like the plat or whatever else is considered to be authoritative. So kind of like in a gray area, and surveyors don't give you assurances of 2 centimeter accuracy on anything. They just say, this is what I measured, and here are the corner points as I determined them.
Yep. We have, you know, part of our property is the road to get to, you know, everybody else's property. And so we had to give up like 30 feet for that. And every so often they go over the thing with a grader. And, you know, I think maybe they caught the tops of some of the markers that were in the ground. So who knows how inaccurate the whole thing was. So
that was all I had. I think Kareem was up next.
I had a question about the before we switch.
Discussion on RTK GPS thing.
Hey, Paul, can I ask you a question before we go to?
Yeah.
Okay. The I know you said there was circuitry in the mowers that you guys have to sense a perimeter fence. Are
Correct.
you planning on using that at all, or
Perimeter wire.
perimeter
Right.
wire? Yeah.
We are not planning on using it.
Okay. Okay. Did you see what I think I showed it last week.
Yeah, I watched your segment where you talked about the wire loop and the sensors for picking up the wire loop. And
Yeah. Is that of any interest to you guys, or does that look a little too simple?
No, because I don't want to have to lay a wire around the property.
Oh, okay.
I mean, that's the whole point of using GPS for mowing.
Mm-hmm. Yeah, but $9, you know, it's hard to beat that. So, yeah, and I don't know how accurately it senses it. It may be another thing of, you know, okay, well, works when the soil is dry, but if it rains out, you know, maybe it doesn't work so well or something. Who knows?
So, I mean, a couple of one of my neighbors, and then Paul Urbanus, who lives just a mile away from me, have got those robo-mows and are using them in their wire perimeter mode, and they work great. You just like offset the wire, because the way it works, you got the front of the mower, and the sensors are on either corner of the front of the mower,
right?
And it knows it's crossed because apparently they put a signal through the wire, and it used the right-hand rule to determine the direction of the magnetic field. And so it's not an electromagnetic signal, it's a magnetic signal. And so by the direction of the signal, they can tell whether each sensor is inside the perimeter or outside of it.
Yeah.
And so if one of them goes outside, then they know they need to stop, back up, turn, and go in a different direction.
Mm-hmm. Yeah, I don't think the one from RoboShop did that. I think it just sensed, you know, an amplitude. So the closer you got to it, the larger the amplitude was. You know, sensing the magnetic field.
Because the ones on these mowers definitely know when they're outside the loop, because you've placed the mower outside the loop, or it like slides, like Paul Urbanus's one has got some steep kind of muddy slope, and it slid a few times and clearly just like slid outside of the, while it was trying to back in, it slid outside of the loop, and then it stopped and it says outside a loop.
Yeah, they seem really cheap. I was going to get one and play around with it just to see how well it did work, but like I said, I'm pretty certain that one, it just sensed, you know, proximity to the wire, not whether you were on one side of it or the other.
And what matters?
Yeah. So anyway.
Well, thanks, Paul.
That was just fine.
Next up, we have Kareem.
Yeah. But how do the teams get beat up?
Kareem, are you there?
I'm here. All right. So, share. So for context, this is are you seeing the sensor?
Yep.
Okay. So this is a video of the sensor, and I'll put the URL in the chat. This is, where did I put that? This is the sensor. So let me back up a bit to where we can see it still. All right. That's good. Drop the sensor.
Drop test.
Right. Yeah. Okay. So you can see the base down here. And then there's this horizontal sensor, like a barrel that's spinning as the other one.
The seam right here.
So inside this,
Oh,
there's
okay.
a barrel sensor that's spinning sort of around this longer axis. So that's what peaks out, and basically the lasers are just turned off when they're facing down. But they also fan out. So it's a point cloud that gives you a full hemisphere. It's very highly concentrated in the center, though. It's directly above it. So I just wanted to give you a sense of here it is running. Oops. So the soft bit, there is so you can see it spins fairly quickly, and again, the internal one is spinning a lot faster. So let me stop sharing that.
Wow.
All right, so here is my robot in RViz. Present something else.
So I'm guessing this is primarily made to face like off the center, like straight out.
Yeah, in my case, so this is the sensor in the model that I've got. So it's looking forward. So it gives me a full hemisphere as of its base plate. In fact, you can even configure it to go another 7 degrees below. So it can go actually wider than a 180 hemisphere. So it's a forward-looking sensor. It doesn't give me anything from behind. If you mount it face up, right, then you're going to get a great image of the trees overhead or the ceiling. Ceiling can be helpful in navigation in certain circumstances, but I like to move it forward because I'm looking for its primary purpose. Well, it'll be involved in both mapping, but mostly it's an obstacle sensor, right? And so I'm trying to calibrate it so that I really understand what's happening on the ground in front of the robot, and really dial it into the maximum accuracy that this sensor can provide. So that's why I'm doing cloud compare. I'm trying to get a sense of exactly where the point of origin is with the sensor, because there's some disagreement about that or fuzziness about that in the documentation and in the test data that I'm going. So anyhow, so like if I turn on the actual cloud, this is actually live right now. So if I turn on the cloud, come on, click. Okay.
Ooh.
So there's the data. So I have it pointed right against this. See this blue section right here? That is a plywood board that I have mounted directly in front of it of a measured distance, because I want to see how uniform the points are, and as well as know exactly, I can compare the distance that I'm getting from the unit to the measured distance between here and the base plate it's mounted on, and see what that correlation is. Because right now it's telling me that the center of the point cloud is actually behind the base plate inside this mast somewhere, right? So my unit is not properly calibrated.
What's the amount of inaccuracy there in centimeters?
So well, that's just it. I haven't gotten to that level of analysis yet, because there's a number of different ways. So one is the calibration could just be telling me that it's got a bad understanding of where the center of the unit is from the firmware's perspective, as opposed to what is the consistency across all of these points on a particular object. And that's where we get into something like cloud compare as a tool to sort of do that analysis. So
was there something to the left of the robot as well, a wall or something?
Yes, there is a that's a whiteboard that just happens to be sitting to the left, and it's not perfectly vertical or anything like that.
Okay. Yeah, it looked like there's something there. It's like it's like another wall.
So this is cloud compare. Are you seeing it? Yeah.
Yep.
Okay, so this is a tool where you can, so this is 30 seconds of data collected by the unit. And it's kind of messy, right? But this section right here where you see some orange stuff, let me turn this off and see if that makes it cleaner. Well, not a whole lot. I think you can sort of detect that there are concentric rings here, right? And so that is the center of the unit. The unit's looking straight ahead at that section, and that right in the center there, that's basically the y-axis of the unit. It's rotated forward, and basically it's the center of all rotation. And it the issue is that it, you know, there's so many other structures it's picking up. So like these are shelves on a book on the wall behind. There's also a workbench. So basically this plywood sheet is attached to a workbench that goes all along here, right? And then there's some shelving above it. And then this stuff up here is actually the ceiling, along with the beams right there for the ceiling. So, and it's a messy, cluttered environment, but the highest density is definitely in this, because I put this board intentionally right in front of it. So that is the item that I want to pick out, and I want to get data on it and measure it. So if I turn off all of the other stuff, so basically what I did was I used a ransack filter, which basically this right here it's basically a shape detection algorithm that just looks through the cloud data, and I asked it to only find planar surfaces, and so if I turn off everything else, and then how come the plane went away? I thought I had it. Plane. Oh, okay. Let me turn this back on. Okay, so that is the actual board. But for some reason, it is still, for the one thing that I was asking about before we started recording was, why is the origin way over here in Cloud Compare when I know the unit is down here somewhere? And that's its actual center of rotation, and there's no other data in this environment. It's just what I imported. So, and I've compared, like if I actually look at the data for the individual points, I can see that really is 0, 0, and 0.6 meters away from the center of rotation. So I know that the real axis for the cloud is here, but I don't know this tool well enough to figure out how to align the cloud's origin with the native origin of the tool, and so then it gives me weird data on its basically on the stats, all right. And I also need to figure out how to filter this down a little bit better, because if you look, can I get it to, if I go sideways here, see how thick this is? If this was properly selected, it would only include points that were like, basically the accuracy on this thing is within 2 centimeters. So it should not be this thick. It shouldn't be collecting that many points. But that may be just a filter thing. Because if I look just, yeah, see, there's a lot that are deeper as well, right? So there's a natural variancy. Again, this is captured over 30 seconds. So maybe this is the best I can expect as far as the accuracy over time from any individual scan. So it's not going to be the kind of thing that you're going to use to scan a 3D object to pull it, make an STL out of it for that kind of purposes, but it should be plenty for, navigation. I'm just trying to dial it in a little bit. So that's all I was planning to ask about. Is if anybody has better experience with Cloud Compare, I'd be happy to learn a little bit about it. Otherwise, I'll keep delving in and figure out what I figure out.
That's pretty cool. That's pretty. I'd never heard of Cloud Compare, but it's a pretty cool tool.
That's a very cool tool. This is a very limited usage of it. You would be amazed at what it can do. Like, people are using it to scan entire neighborhoods, or analyze the data from overhead drones flying the really high-end solid state LiDAR scanners over neighborhoods, and detecting ground beneath tree cover and all sorts of stuff.
Oh,
Can
wow.
it blink an LED though? That's the question.
Yeah, maybe not.
Maybe not. Okay.
So,
Kareem, I've got a question. Just looking it up on Google.
Yeah.
Did you try to edit the global shift and scale? Is what it's telling me in the DB tree.
The global, I haven't even seen that, but I haven't seen
So
anything like that.
Select the point cloud in the DB tree, go to edit global shift and scale, and you can manually override the global shift coordinates or clear it to 0, 0, 0. That's just what I got in a Google search here, just quickly.
Yeah, I don't see a global shift in scale cloud here.
It's not the first time Google steers me wrong.
Google's, yeah.
So that was method 2, and I looked at that because it seemed to be the simplest.
Yeah, not seeing anything that looks like that right now.
Yeah, select the point cloud in the DB tree and go
Yeah,
to
I
edit.
did.
Okay. Edit the global shift and scale. So that's just, I thought I'd just give it a quick check.
Yeah, I'm not seeing those options.
Okay.
Here.
So Kareem, what's the price tag on that unit?
About 400.
Oh my God.
If you think about it in terms of a per point cost, it's way lower than the limited view TOF sensors that a lot of the clubs are using. Even the ones that got like a 64:8 grid on them, it's like this is completely different category. But it's also a physical unit, and it has vibration issues and things like that. So it have some issues with driver support, tool support from the company that produces it. This is produced by the same guys who do. I'm drawing a blank on their name right now. Big Chinese robotics company. The guys who, we saw their wheeled rover at the last in-person.
Unitree?
Oh,
Unitree. Yeah. This is a Unitree. This is the unit they have on those dogs.
Oh, in the front of the dog. Huh?
Yeah. They're just pointed. They're pointed down in that case because they're trying to find footfall locations for the legs.
Yeah. That sounds like a great justification to your wife. Honey, the cost per point is much less than these other units.
Exactly.
It's a fraction of the cost.
It is totally a fraction. Yeah. I mean, it's the same thing that happened with cameras, right? So cameras cost almost nothing per pixel these days.
Yep.
Oh, it's a stupid mask on it.
Thanks, Kareem.
Sure.
Let me know if I forget to mute my mic, guys, because it's noisy here. That was it for our presenters.
I came across an interesting thing that I thought I'd share with the group, relevant to some of what some of us are doing. So it came across one of the robotics news things that I subscribe to, and it's a course that ETH in Switzerland, it's got a big robotics group, and they've made an online course. Well, it's not really an online course, but they put the videos online, And this guy Oyer Mies is the lecturer. He's done some amazing stuff in the course of his fairly as yet short career. So I watched the I watched the first lecture, and it was really an interesting and good overview of what they're going to do cover in this course and the techniques. So they covered he talked about imitation learning versus reinforcement learning, and the slides are not available for download or viewing, but you see them if you watch the video. So effectively you're getting the lecture part of the course. Now not getting the TA assistance or the projects, the homework, or that kind of stuff. But then they go in. So those, and he's kind of framed it in comparison to how LLMs have progressed in terms of learning from huge data repositories, and robotics doesn't really have huge data repositories. So imitation learning and reinforcement learning are two ways of trying to do without that. But then he's going to get onto generative models and some of the more advanced stuff that's like only a year old. So anyway, really neat. I'll put this link into the chat, but looked like a really fun and interesting set of lectures. That was it.
Well, thanks, Paul. Does anyone else have something they'd like to share tonight? Well, I guess that's it. It was a very good meeting, guys. Lots of interesting stuff to digest. Hopefully we can keep this up. A couple really good meetings so far.
Yep. Yeah.
Okay.
Cool. See you guys.
Good night, everyone.
Good night.
Good night.